let X be a sober topological space. Sober. Okay, so we'll say that we'll give a definition. So for P in X, a point P prime in X such that P is an element of the closure of this point, and sometimes we'll just call this like this, is called a generalization or sometimes we'll call it a deformation of P. Okay, so this is kind of this whole specialization, generalization thing. Let me tell you what we're thinking about here. So let me give you the picture. So the picture is as follows. So here's X, and so we can take some. So Y. So this can be some closed, irreducible subspace, and so we're thinking of schemes. So really, sober topological spaces are the underlying topologies of. So the underlying topological space of a scheme is a sober topological space. This is also true for algebraic spaces. I haven't posted anything on the channel, but this will probably come soon. Okay, so here's the thing. So we have X and we have this closed irreducible subspace, and so there's kind of this whole thing we can think of the generic point. A to Y is the generic point. So sober topological spaces have notions of generic points of Y, and so the closure of this point is going to be Y itself. So this is the idea that the closure of this is Y. Okay, this is what we have, and so okay, these are what generic points do, but so we could. What this definition of being deformed is that you have this thing, and then when we take its closure isn't necessarily in. Well, we can put it in some family here, right? Such that that maybe this point here is the generic point of the family, and it's not completely contained in Y. This is the idea. So this is a point. This is this thing deforms P outside Y. That's the idea. Oh. Let's get rid of that. Okay, so we have this now. Now I want to state a lemma. The lemma says the following. So let lemma. Let's take X to be a sober topological space. So this is not necessarily Noetherian. And we'll have the following equivalence. So X is going to be irreducible as a topological space. So this is that it has a generic point if and only if X has the deformation property. Has this deformation property. Let me explain what this is. So by the deformation property, I mean that for every closed subspace, then every point in the closed subspace, there exists some Y prime, such that Y prime deforms Y away from Y. Okay, and again, this is this picture. So this is the lemma, and the picture is that we have this thing. We have some Y prime. Here's X. And we have things in here, but we can find, so here's Y, and then we can find some generic point, maybe Y prime, so that that's outside of X and whose closure outside of Y and whose closure contains Y. That's the idea. Okay, so let me grab some paper here. And now I think we're ready to prove this. So here's the proof. Oh, maybe I shouldn't have folded this up. Or maybe I should have. Okay. So the proof is the following. Okay, so we're going to take x, and we're going to do two things. So first of all, we'll here. So suppose we'll do this direction. So this is the forward direction. We suppose x is irreducible. So this is with respect to the deformation property. Oh, sorry. Okay, so let's do this. So we want to show. So we want to show now that there's this deformation property. So we have an irreducible, and we want to show this. Okay. So what we'll do is we'll have to take two things. So we'll take y here closed. Okay, and then we need to take some y and y. Okay, and we need to show that that we can deform this point outside of x. But so x is irreducible. Okay, so what we'll do is we'll take eta of x. This is going to be the generic point of x. And clearly we have x being the closure of its generic point. Okay, and this certainly contains y. So this contains y. And eta of x is not contained in this proper closed subspace, because if it were, then it would be, the closure of this would be contained in the closure of this, and in particular x would be a subset of y, so they'd be equal. Okay, and that proves this part. Okay, so we have this direction. Let's do the other direction. Okay, so suppose x has the deformation property. And so what do we mean by this? We mean that for every y, right, we can in every closed subscheme we can find a point that outside of the closed subscheme which deforms it. So we suppose that we have this property here. Okay, so we suppose we have this deformation property, and so again. So what we'll do is now we'll suppose that we have a decomposition. Okay, so there always exists. So a fact that we'll use is that even for non-Noetherian topological spaces, there always exists maximal irreducible components. Okay, so this is like a Zorn type thing. And so we'll write x is equal to y1 union y2. So it's going to be the union of two things, where y1 and y2 are closed subspaces, and y1 is an irreducible component. Okay, and again, this works in the non-Noetherian setting. Okay, so by hypothesis, so we're supposing that x has the deformation property, and we want to show that x is irreducible. Okay, so okay, so let eta 1 be the generic point of y1. Okay, if y1 is, okay, so if y1 is not equal to x, then so this would mean that it's closed and it's not contained in X. So, and we have this point in here. So then there exists some eta 1 prime, okay, outside. This is by the deformation property, outside of y1, such that eta 1 prime is contained. So eta 1 prime contains eta 1. In particular, eta 1 prime, this thing here, so this is in y2, okay, and this is closed here, and so we have that this is here, and this contains eta 1, right? So this means that it has eta 1 bar, so this is here, and this is actually this is equal to y1. So here, this is no longer maximal. Okay, so this is not maximal. So this gives a contradiction that y1 is a maximal closed subscheme. Okay, so this is the contradiction, is that if we write y1 as an irreducible component, then by taking this generic point and deforming it outside of y2, outside to y2, we'll end up getting that y1 must be contained in y2. Okay, so then this gives us a contradiction. Okay, so that we'll have some other piece inside there. Okay, and so that proves our lemma, that this deformation property is the same thing as irreducibility.